Okay, the last part of this chapter, we're going to do more with correlational analysis. So researchers often wish to examine the strength and the direction of a relationship among two or more variables. We have the correlation coefficients and scatter plots. The manner in which performance on one variable may be predicted from another variable, we can look at regression analysis. Correlation coefficients are accompanied by some statement of statistical significance of the index, whether the correlation coefficient is significantly different from 0. And this is a statistic known as the index of determination, or R squared. The square of the correlation coefficient gives an indication of the actual amount of overlap between the two variables in terms of shared variance. With correlational analysis, remember we're not applying cause and effect. That would be with inferential analysis, which we'll talk about next chapter. If variable A and variable B are correlated, that means they correlate or they vary together in some describable way. As one variable moves in one direction, the other tends to move in the same direction. That would be a positive. Or in the opposite direction, a negative relationship. One does not necessarily cause the other to vary unless the relationship is perfect. With correlational analysis, it allows the researcher to make predictions of the value of one variable from the knowledge of the variable of another. Independent variables can be our predictor variables, and dependent variables can be our predicted variables. The researcher then sets out to find the best linear combination of the predictors, one that acknowledges the unique relationship of the predictor with the criterion. It minimizes the overlap, the correlation among predictors, and maximizes the combined strength of the predictors. We would use multiple regression analysis, which mathematically determines the order in which the predicted variable should be entered into the prediction equation to maximize your prediction. It assigns weight to each predictor variable, and then there's a stepwise multiple regression indicates the contribution of each new added variable to the predictive validity of the equation. The success in meeting of multiple regression analysis depends on a number of factors. The care and the selection of the initial variables, the reliability and the validity of the variables being measured, the size and the representativeness of the sample used, the reliability and the validity of the criterion measures, and the practicality of gathering all the predicted data appearing in the equation. When we're analyzing relationships, the scatter plot graphically depicts the relationships between the two variables. It shows the intersection point of the two measurements for each subject. If the two variables are positively correlated, the subjects will tend to have higher scores on both measures, medium scores on both measures, and low scores on both measures if the pattern of the dots slope upward to the right of the graph. If the two variables are negative related, the subjects who score high on one variable tend to have low scores on the other variable, and it slopes downward. A tight cluster of dots equals a strong correlation. A diffuse cluster, diffuse pattern, is that weaker correlation. Several variables could be studied simultaneously rather than just two at a time, so you could do multiple correlation studies. You can have correlation coefficients calculated for all possible combinations of two variables, and then you could display it in a matrix. You would use the Spearman rank order correlation if you wanted to rank order the data using non-parametric statistics. You could use contingency tables if you're using nominal level data. That very simple where it's this or it's that. Two-dimensional frequency distribution. Contingency tables are usually accompanied by further data to determine whether a significant relationship existed at all between the variables, and that would be a chi-square or a contingency coefficient. There's like a summary table I'm going to give you at the start of next chapter that will help you kind of more visualize what statistic you would use with what, like non-parametric or parametric, whether you're looking at relationships or inferences. So it'll be organized or a little bit easier to understand when you use what when I have this table available for you. So like I said, it'll explain the chi-square, the contingency coefficient. Again, whether your data is nominal or null, interval or ratio, whether you're using parametric statistics or non-parametric statistics.